Here is a rectangle. Its length is 3 meters more than its width, and its area is 40. What is its perimeter? Give this same problem to one language model 8 times. It produces 8 different responses. 2 end with 26. 5 end with some other number. 1 never reaches a final result. For this problem, the correct final result is 26. So a checker gives each response ending with 26 a score of 1. It gives every other response a score of 0. It does not examine the algebra in between. Now the training problem is precise. The model produced each response 1 token at a time, but the checker supplied only 1 score for the entire response. How should that 1 score change the probability of each token? Before answering that, we need to understand what a score of 1 means here. So let us look at all 8 scores together. Now they are together 1, 1, and 6 zeros. All 8 came from answers to the same question, so we treat them as one group. Start with the average. 2 total points across 8 responses gives 1/4. Now subtract 1/4 from each score. For A and B, 1 minus 0.25 is positive 0.75. For each of the other 6, 0 minus 0.25 is negative 0.25. Next, measure how spread out the 8 scores are. Their standard deviation is about 0.43. Divide each difference by that number. Positive 0.75 becomes about plus 1.73. Negative 0.25 becomes about minus 0.58. These final signed numbers are called advantages. A positive advantage means that a response scored above the group average. A negative advantage means that it's scored below. Why is the positive value larger? Only 2 responses received a 1, while 6 received a 0. 2 copies of plus 1.73 balance 6 copies of minus 0.58. Before rounding, all 8 advantages add to 0. The average 1/4 is the baseline for this question. We now have 1 advantage for each complete response. But the model produced each response 1 token at a time. How does 1 advantage change all those token probabilities? Answer: A now has an advantage of about plus 1.73. Look inside that answer at the moment the model produced the token 5 in width equals 5. Immediately before 5, the model had the question and all the earlier tokens as input. From that exact text, it assigned a probability to every possible next token. Suppose the probability of 5 was 0.1. The model sampled 1 token, added it to the text, and calculated a new set of probabilities for the next token. It repeated this process until the response was complete. The probability of producing this exact response is found by multiplying the probabilities of all the tokens the model sampled. Take the logarithm, and that multiplication becomes addition. Now 1 log probability term sits beneath each sampled token. Bring back the advantage. The same plus 1.73 is attached to every sampled token in A and B. The same minus 0.58 is attached to every sampled token in C through H. A positive advantage tells training to make those sampled choices more likely. A negative advantage tells training to make them less likely. But the probabilities do not all change by the same amount. Every token was calculated from different preceding text and began with a different probability. So 1 model update affects each of them differently. The advantage supplies a common direction, not an identical change. Together, all these next token probabilities are the model's policy. The group comparison produced the advantages, and those advantages now direct an update to that policy. This is Group Relative Policy Optimization, or GRPO. It tells us the direction of the update, but not how far to move. For the token 5, should 0.1 become 0.11, 0.13, or 0.5? That is the next problem. Suppose training changes the probability of token 5 from 0.1 to 0.13. Keep point 1 visible. It is the probability assigned by the version of the model that generated these 8 answers. Call that version the old policy. 0.13 comes from the version now being trained. Call that the current policy. Now divide current by old. 0.13 divided by 0.1 is 1.3. This is the probability ratio. It says that the current policy assigns token 530% more probability than the old policy did. Answer A has a positive advantage, about plus 1.73. Before applying any limit, this token's contribution is its probability ratio multiplied by its advantage. At a ratio of 1.3, that contribution is about 2.25. But suppose continued training on these same 8 responses moves the probability of 5 from 0.1 to 0.5. The ratio is now 5, and the contribution becomes about 8.66. Nothing new has been generated. Nothing new has been scored. The same response is producing a much larger contribution simply because the current model has moved farther from the model that generated it. So this group gives us a useful direction, but it should not support an unlimited change. Once the current policy has moved far enough, we need fresh answers and fresh scores. For this update, mark an illustrative range from 0.8 to 1.2. Start with A's positive advantage. Its actual ratio is 1.3. Keep that actual ratio. But when calculating this token's contribution, use 1.2. Any further increase receives no larger contribution from this old response, so the graph is flat above 1.2. Now stay with the same group and look at a token from answer C. Its advantage is negative, so training favors a smaller ratio. That improvement continues down to 0.8. Below 0.8, use 0.8 when calculating this token's contribution. The graph is flat below 0.8. This stopping rule is called clipping. It limits how strongly one previously generated group can affect the next update. It does not force the actual probability ratio to remain inside the range. Once this update is finished, do not continue using the same 8 answers. Use the current policy to generate a fresh group, score those answers, and repeat the calculation. The current policy now fills the 8 empty cards with fresh answers. They need not match the previous group. Changing a token probability changes how often a choice appears. It does not guarantee the next answer. Then repeat the same calculation. Score the 8 answers. Find their group average. Convert each score into an advantage. Apply the clipped update. Use the updated policy to generate the next group. But why generate several answers to the same question? Return to the first group. 2 scores were 1 and 6 were 0. Their average 1/4 became the baseline. We could calculate that baseline only because we had several scores to compare. There is another way to obtain a baseline. Train a second network alongside the language model. Give it the question and a partial response, such as the text ending at with equals. Its job is to predict the score that the completed response is expected to receive. That expected score predictor is called a critic. The token policy can then compare the received score with the critic's prediction before applying a clipped update. This policy and critic setup is the language model form of proximal policy optimization, or PPO. GRPO removes the trained critic. Instead, it generates several answers to the same question, scores them, and uses their average as the baseline. So GRPO does not train an expected score predictor, but it must generate multiple completions for each question. It also still needs a scoring system to assign the final scores. That is the exact exchange. No learned critic, but several scored answers to the same question. And this replacement works only when those scores differ. What happens if all 8 scores are identical? The all 0 group is already on the plot. Its average is 0. Subtract that average from every score, and all 8 advantages are 0. This group produces no update. Now move every score from 0 to 1. The average moves to 1 as well. Subtract again, and all 8 advantages are still 0. The scores changed from the lowest possible value to the highest, but their differences did not change. There are no differences. GRPO needs score variation within the group. Bring back answer B from the original group. It ended at 26, so the checker gave it 1, and its advantage was about plus 1.73. But B says the width is 8 and the length is 5. That contradicts the condition that the length is 3 more than the width. The checker received only the final result, 26. It received no information saying that the earlier dimensions were reversed. So the same positive advantage was attached to every sampled token in B, including the tokens for width equals 8 and length equals 5. We can see the error by reading the response. The score does not contain it. The all 0 group reveals a separate limit. Here, all 8 sampled answers are wrong. None shows the model a successful way to solve the problem. A correct answer must first appear in the sampled group before this update can make its sampled tokens more likely. Now we can answer the opening question. One final score reaches many tokens because the log probability of a complete response is a sum of token log probabilities. Scores from the other answers determine whether the shared advantage is positive or negative and how large it is. The old to current probability ratio and clipping control how strongly that group affects the update. The group average supplies the baseline without a learned critic. But none of those calculations adds information that the scoring system did not provide. With this final answer checker, A and B look equally successful because both end at 26. GRPO can identify which sampled responses scored higher than their group. By itself, it cannot identify which algebra step made a response valid or invalid. One final score can tell training that a response did better. It cannot tell training which token deserved that score. That leaves one practical question. What additional information should the scoring system provide so training can distinguish correct reasoning from an answer that only ends correctly? Share how you would design that signal in the comments.